Offerings. Been with Holy Cross Energy now for 5 years. I started out as a design engineer and then moved into system ops, and have spent the last 2 years in a very, very unique role, which is a research engineer. There's not too many research engineers in the co-op field. My main goal is to engage in government grants and research projects, define the use cases that pertain to our utility and our industry, perform the research, and then take the lessons learned and kind of turn that into programs and operations for our utility to grow with. So if you're not familiar with Holy Cross Energy, we sit on the western slopes of Colorado. We're a member-owned, non-for-profit electric co-op. We have about $130 million of revenue, 160 employees. Our winter peak happens mostly around Christmas, somewhere between Christmas and New Year's every year, about 160, 170 megawatts. You know, as contrast to that, our summer minimum can hit as low as 80 megawatts. So this is our May and September time chains, where loads are extremely down, and you know, generation, especially local generation like PV, can be extremely high. So we're starting to prep for that. Last year, we were able to accomplish a 44% RE mix on our distribution system, and we're gaining on that. We cover the area from Vail to Glenwood Springs. Then we'll also cover the Highway 82 corridor from Glenwood Springs to Aspen, part of the 133 corridor, and even some small sleepy towns like Marble and Thomasville. And then we also have a little bit of mixed territory with Excel, where we cover the south side of I-70 west of Glenwood, and Excel covers the north side of I-70. So it's a little bit of a polka dotted territory, but it's a good territory. It's very mountainous, it's very challenging and sometimes, but it has led us to a lot of opportunities. 2018, our board of directors set a clean renewable target of 70% renewable energy, as long as 70% reductions in emissions, all by 2030. This has been a great mark in the sand for us to base our ideas around, design new rates around, and find new programs that can help us meet all these goals. So this is kind of the evolution of our fuel mix. In 2015, you can see that we're heavy on coal, as we own 8% of Comanche 3 down in Pueblo. That asset's mostly owned by Fiesco Public Service Company of Colorado, doing business with Excel, but we do have a small ownership in that. But you can also see in 2005, we were heavily reliant on natural gas, and our renewable mix was very low at 7%, a little bit of hydro that we had locally and some wind that we bought into. By 2018, we'd reduced our use of fossil fuels and natural gas, and we're slowly starting to clean up our supply. So we went from 39 to actually 44. And as you can see, in 2024, this is our projection energy goals. This is what we're trying to hit by 2030, and hopefully we can hit it soon. But a lot of this is based on intermittent power. A lot of this is based on wind that blows at night and solar that shines in the day. And as you can see, what I call our green Pac-Man here is just gobbling up all these fossil fuel goblins. I think we can get there, but it does create its own challenges of how to balance the grid in a high DER and high renewable energy scenario. So to conquer some of this, knowing that we were going to be able to get to 70% fairly soon, and knowing that the next goal, or the next line that was to be accomplished, was to figure out how do we get up to the 80 or the 90 percentile, or maybe even that momentary 100 percentile, we started to get involved with some research projects. A lot of this had to do with Brian Hannigan, our president and CEO, coming over from the National Renewable Energy Lab. And with then came over some opportunities for a utility like Holy Cross to get involved with research, and then help mold the industry with our vision of how that needs to be done from a cooperative level. So along came this project in 2018. We did a lot of modeling efforts where we took our distribution and then gave them the whole grid that we had and built a digital twin over in Golden at the Energy Systems Integration Facility there at NREL, and then just started doing some analysis. But as part of that project, we were looking for a field demonstration. We had worked with Habitat for Humanity of the Roaring Fork Valley on their prior project where they built their new Restore 2.0. Kind of near our headquarters, and we had heard rumors of an affordable housing community that they were also developing. They really led this effort along with Pickens County and the Basalt School District and other companies like CORE that we have here in the Valley to find a way to allow our teachers and our county workers to stay and live where they wanted to, where they worked. The problem with Basalt and the problem with a lot of mountain towns is the cost of living and the cost of housing are just through the roof. And if people want to come and live here and have a life here, it's really hard for people to own houses or even to be able to rent. So you end up with a little bit of a transient population. And we noticed that the average house in Basalt costs around $700,000, and these teachers are making, $50,000, $60,000, $70,000 a year. So buying a house and trying to live near where you work was almost impossible. So Habitat came around and decided to do this project, and it took a lot of effort from a lot of different community partners to build these 27 homes. During the design phase, when we were still doing the architectural analysis and some of the engineering studies, one of the board members, Autumn Schindler for the town of Basalt, walked into a meeting and really kind of planted the seed of what it would mean to go all electric again. And being in a utility, you understand what it means to be all electric. I live in an all electric house. It was built in the 1970s. I'm pretty proud of that. I'm familiar with the energy revolution, where we gained our energy independence in the 1950s and we had an electric boom. But this was the first time I'd seen it come around in the late teens and early 20s, where people were talking about all electric homes again, or net zero energy homes, or totally electric homes, whatever you want to call them. But this was really a good test for that. By not bringing in the gas line, we were able to save around $30,000 just by not bringing it across the street. And then the cost of wiring these houses with all electric is very comparable for the same price of metering and bringing in gas lines to each individual house. So with that in mind, that we were going to try to build an all electric community, it was thrown on the table. Let's try to make this a net zero energy community. Let's try to build a community that can create as much generation, how much energy as it needs in a year that it consumes. So here we are. I'm looking for a field deployment project. I got this great partnership with Habitat for Humanity to go in and try to build an affordable housing community, and everything just kind of clicked. So we looked at these houses and we went in there and we were looking for controllable loads. So we looked at, what do we want to control? We looked at PV that was on the roof. We looked at battery energy storage systems that we put down in the basement, mobility charging, EVSCs, which were put in the garages, and what I've come to start calling comfort. So this is hot water heating and HVAC. So the case study that we got involved in was to demonstrate the ability for us as a small co-op to signal a DER, to send it a command and have it respond, mostly based on economics, but also not only the economics as our utility as a whole, but also individual economics. So the way we did this is we put 5 DERs in each house, and those DERs are like I talked. We got PV, batteries, water heaters, EV chargers, and air source heat pumps. And from this, we coupled microgrid controllers. The microgrid controllers were based out of a company called Gila Technologies. They're based out of Boston, and they design a hardware. And it's a small black box that couples with any DER. And what it allowed us to do was to build what we know as flexibility now. It's a pretty big buzzword, but it's definitely the right word when talking about a building that's integrated into the grid. Also, as part of this, we built what's known as an advanced distribution management system. So this is the system that sits in dispatch that has a situational awareness of what's going on all the grid. It also has situational awareness of what's going on just at Basalt Vista and can send it commands. And we'll get into these commands here in a little bit of what actually goes on out there. But the other advantage of having an ADMS sitting on your system is that you're able to build a bunch of systems together, and this is known as interoperability. But by the end of the day, what we had done was built what's called a resilient soft microgrid. So it is a house that is able to microgrid by itself, but the 4 homes aggregated together work better to perform grid functions. So that's why we call it a soft microgrid, because it has the ability to microgrid, but it works better when it can get what's known as the pulse from the grid, so the frequency and the voltage. When it has those two and it doesn't have to synthetically make it on site, it's able to perform at a much more economic scale. So a little bit more about ADMS here. Most people call them SCADA systems, but they're kind of the one step up from a SCADA system. Once you have a SCADA system and you incorporate your outage management system, and now this DERMS, this distribution energy resource management system that sits on it, you kind of have three systems in one, and that's why it gets the word ADMS in front of it. It is an advanced system. But what's really neat is this bottom right-hand corner. And what we did was we put metering at the transformer. So all 4 homes, now 9 homes that we saw in the picture on the first couple of slides, are connected to one transformer. And at the transformer, we read voltage, amperage, kW, power factor, and VARs at a 1-second interval. And what we have sitting on the transformer is a coordinator. And that coordinator, it was made by Hewlett Technologies. And in my opinion, he's the pit boss out of there. He's the only one that takes a command from Holy Cross and performs an action. So again, all 4 houses, each house has 5 DERs in it, so 20 DERs, and each DER has a microgrid controller. And then on top of all 20 of those DERs is one microgrid controller called the coordinator that I talked to. So I can make calls to the coordinator. And that's what you're seeing over here. We based our design on 3 modes that you see. Optimization mode. Optimization mode runs an OPF algorithm. That's an optimal power flow. And that is a simple algorithm. It's a mathematical equation that takes the information that it knows from the transformer and changes the set points on inverters or EV chargers, or even can turn down the thermostat. A lot of this is kind of next generation of energy optimization, and that's what I call this presentation, because that's what we're really doing here. For the last 50, 60 years, we've been working really hard on energy efficiency, and we still practice that every day, especially at Basalt Vista. You can't really get into energy optimization until you've really made a tight envelope where you've made it efficient to optimize that energy. The next step, as you see with Basalt Vista, and as you're seeing around the nation, is what's known as beneficial electrification. As our grids get greener, what all can we convert into electricity so that we're not burning fossil fuels and polluting anymore? The next step above that, in almost a little subcategory of BE, is energy optimization. And that's how can we optimize energy on the grid so that we can move loads with the same dexterity that we've always moved generation with. And that was kind of the main thought behind this. In 2018, we experienced what was known as the Lake Christine fire. It started on July 3rd and burned for 3 months. It burned 13,000 acres. It took out 3 out of our 4 transmission lines going into the Roaring Fork Valley, and gave us probably one of the biggest scares we've had to a blackout, not a power outage, but an actual blackout, probably in the history of 80 years at Holy Cross. From that, we designed a distribution system where we're able to put it in modes. So when we get a red flag alert in our distribution system, we change our protection scheme. We make our protection open up a lot quicker so that we don't create fires from fuses. This has been great for the last couple of years. This winter, we also implemented a snow watch so that when we're predicting heavy snow coming in, we can change our protection settings across our whole system to give us a better advantage of battling snowstorms and outages. So we took that same mentality and applied it to the 4 homes. We said, well, what if we put these 4 homes in a mode? Well, what modes would we want them to be? Well, the first mode was pretty simple. We want to optimize. We want to optimize the energy not only consumed, but the energy produced by the 4 homes as an aggregate itself. This runs the NREL OPF algorithm, the optimal power flow algorithms that we talked about. Again, one algorithm sitting at the corner, or coordinator, and then one algorithm sitting at each one of the DERs. And the beauty of this algorithm is it's the same algorithm. So when you put it into optimal power flow settings or optimization status, it runs those OPF algorithms. And the main purpose is to arbitrage time of use. It was great to hear that your next call is going to be with Fort Collins. to talk about behavioral response to time of use, because this is the polar opposite. So be good for you guys to have this in your back pocket as you go into that conversation. The next mode that we're able to put the system in is known as peak time management. One of the things that we've been doing for a couple of years is forecasting our load and forecasting our peak and being able to try to mitigate by that. Some of the programs are done with behavioral response, where you might get a text message or an email saying that there's a peak event tomorrow night between 6 and 8 p.m. Reduce your load and make some money. It's the same concept here, except we're not sending you a text message. I'm calling up the coordinator and saying, hey, how much available power do you have on the system? And I want you to push it onto the system between 6 and 8 p.m. The third mode that we got into was storm watch, and this was taken exactly from the Lake Christine fire. We want to push as much energy as we can into the system in response to an outage. Now, this could be an outage that is scheduled, where linemen are going out to change a transformer. It can also be something where we expect some snow load coming in, and we just want to push as much energy as we can into the house, into the batteries, into the EVs, into the hot water tank, preheat the air conditioner or the heater a little bit. But what we found out, what became really cool, was what's known as a watts in a box now. So in that box right there, I can type in a number, and it's not an unlimited amount of number. I can only call for as much watts that are out there, but I can type in 3,000 watts into that box. The 4 homes together will aggregate and give me 3,000 watts across the transformer. Me as a system operator, I don't care which devices are giving me the power. All I care is that I made a power call and the 4 houses reacted with the set power call. The other thing I can do is I can put a negative number in here. So I can type in minus 3,000. And now the 4 houses together will aggregate and consume 3,000 watts. So charge the batteries, charge the EVs, curtail the PV, whatever the 4 houses need to do to try to exactly match that. Well, this is where it gets really cool, is that you can put a 0 in that box. And now the 4 houses will aggregate together to try to send 0 power across the transformer. Again, still taking the voltage and the frequency from the grid, but not consuming or delivering any power. They have aggregated themselves. They are truly, for an instant, a net zero instantaneous home. So this is a 3-day trial we ran. The first day, as we talked about, it's just normal. You can see some air conditioning or some heating load coming on in the morning, and then you see a whole lot of solar generation. And then you see how a normal day progresses when people come home and the sun goes down until the next day, which we ran peak load management. We literally took the sunshine from that day and discharged it in the grid between 6 and 8 p.m. This is, a direct hive, just charging the batteries and then setting the forecast to discharge between that time. And at that point, I make a call out into the system that says, give me as much power as you possibly can. There is no set value. On the third day, we ran optimization, where we set the transformer at 0. We still allowed the PV to generate into the grid because these are net metered, but the 4 houses together never went above 0 consuming during that time. And as you can see, we ran into the night, ran into almost 6:30 in the evening. Here's some overlays of what it looks like when you move around energy, and that's exactly what we're doing. This is just overlays from the day before. You can see on the orange graph on the left-hand side, about 2 o'clock in the morning, we did some EV charging that day too. But this is just us moving energy from the sun to the nighttime when we need it. This is the overlay on optimal power flow, just showing how much energy was stored and then used later. Again, we could have set this directly to 0 and had no output onto the grid, but because of PV and we're working on our RE numbers, we're pushing onto the grid. So some of our biggest lessons learned from this project was to focus on the big 3, PV, EV, and battery energy storage systems. I think once you have control, especially over EVs and batteries, that there's not a whole lot of added value to manipulate people's comfort. Changing a couple degrees on a thermostat is a drop in the bucket to charging 10 kW of battery as well as 7 kW of EV. Yeah, The other comments here is that DERs work together in small groups to provide virtual power plants and microgrids. And this is kind of a vision in the future where we're able to cluster DERs. So if you have a situational awareness where you understand what exactly is going on the grid, you're able to know where these DERs are located and cluster them together to either perform a microgrid if you need it in a resilient situation, or this kind of next step up where we take not only net zero energy homes, but we turn that more into a net zero energy zone, where you have a group of homes or a community or even a subdivision that can run those OPF algorithms, and during times when you need it, not provide power to the grid or not take power for the grid. So that's coming. The other huge difference is, especially for utilities, is that we do have access to low capital. So, providing on-bill payments with low capital to support DERs, having access to that low-cost capital has really made the material difference. You should hear something like that from Fort Collins next week or whenever on their battery project. As I said, we built what's known as our digital twin at the NREL facility. NREL is full of some very smart people, and they took all of our 2017 data, every single AMI read that was on the system across our 60,000 meters. And then we also gave them every substation point on a 5-minute read. We started running simulations. The nice thing about having a facility like NREL is that a simulation that would take a year to gather the data, they're able to do in 3 or 4 days. So this bottom right-hand corner is what you're looking at is what happens when you take PV and stick it on every home on a feeder. So a feeder is one line from a substation out to a point. On this feeder, there's about 1,200 homes. This comes out of Basalt and goes into the Snowmass Capitol Creek area. And what you can really see here is that you end up with voltage violations, but you don't end up with voltage violations across the whole feeder. You end up with the clustering of voltage violations. So as you can see, the black circles above the red line is one neighborhood. And what this shows you is that utilities, maybe not even utilities, if you would have asked me 2 years ago how many DERs we needed to control, I would have told you all. But based on the work that we've done at NREL, you're only looking at 20–25%. And what you're going to find out is that every feeder that you have is going to have its own unique and problematic area, where it'll be advantageous to go in there and build in utility scale controls to alleviate this. Some of this might require flexible interconnections and flexible generation, where you can curtail PV and people still get paid for it, or there's a first in, last out kind of hierarchy that can happen here. But it will come as we end up in these high penetration scenarios. The other comments here is that computing and coordination is best done at the grid edge. That's a lot for timing. At Basalt Vista, we were able to do 1-second reads on that transformer like I talked about and send that over to the coordinator so it can make quick decisions on what actually was reacting and providing the power when we make a power request. If you take that same signal and you send it all the way back to your distribution center and then make the decision inside a computer there and then send it all the way back out to the grid edge, it's fast, but it's 5, 6, 8 seconds fast. It's not 1 second fast, and that can make all the difference when you're trying to figure out how something, a DER, is reacting. There is a need for multiple and redundant communication systems. That's more of an approach to resilience. We know that Wi-Fi can go out. I hope I'm still broadcasting to everyone right now. We also know that cell communication can go out, especially during power outages. So there is a need to make sure that these systems are able to communicate, especially if they're starting to microgrid. So these are our program offerings that have come out of a lot of work that we've been doing over the past 2 years. The top 2 are kind of how we fund DERs right now. And I'll just use a battery, for example. So as part of this project and part of our EV work, we decided to develop a service agreement. So this allows us to finance a DER and spread the payments out over the warranty of the DER. So for an EV charger, we allow this for 3 years, which matches up to the EV charger warranty. But for a residential battery, we have the ability to make on-bill payments for 10 years on that. So that can dramatically reduce the upfront cost. The next program, called Distribution Flexibility, or DF for short, is our ability to credit for a DER to access the control. So like Fort Collins is going to talk to you about, and like a lot of other people talk about, there's behavioral response, and then there's autonomous response. So behavioral response is this peak time payback in what we'll know as dynamic renewable pricing. Again, that's where we send a signal out to the member and ask them to decrease load for the PTP. But, you know, as we talked about early on, there's going to be times in May when my generation gets above 70, 80%, and that's on average annual. So that means in May, when my loads are down, I'm going to have oversupply. I'm going to have more electrons than I know what to do with. So we got delayed a little bit. This is starting March, but we're going to start this in Q3, maybe even Q4. We're going to see what the appetite is out there on the system to increase load. So again, a forecasted event, maybe we have too much wind. We're in a PPA, which is a take or pay. So we really don't want to curtail. We'd rather take that energy and find places to put it. And that's what the dynamic renewable pricing is going to consist of. But those are two both behavioral response programs. The distribution flexibility program takes it one step above that. And that says, I have a DER asset. I trust my utility. I'm going to hand over the keys of that asset to the utility. And then we can pay them for that. And in the payment for the DF is much higher than the peak time payback because we know the DER asset's always there. With peak time payback, time of use, and behavioral response programs, you end up with known as a saturated load shape in the summertime. You get to a point where your members or your consumers are generating or consuming just about the same much energy on a Tuesday as they would Wednesday and Thursday. So we end up with these hot days, just like today, where it's 90 some odd degrees out, the humidity is well down, and we expect that the same temperature is going to go for the next 3 days. So as a utility, it becomes really hard to predict which day is going to be my peak. And what we have found out through the peak time payback program is that on day one, people respond very well. On day two, you get less response. And by day three, if you have 3 events in a row, people are burnt out and you don't get response. But the distribution flexibility tariff completely changes that. It allows us to push a button and discharge a battery without the consumer even being affected by it. Most people don't know which way their meter's spinning. If this meter's spinning back into the grid during 6 or 9 p.m. and they're living off their battery and we're getting benefits from the battery, that's where we've been able to design this program and been able to pay out about 10 times much per month than the peak time payback would pay. And that's because the DER is always there and it's waiting for us to signal it. We also have a time of use and then our green pricing program called Pure. Pure, it's a great program and it allows us to get more renewables onto the grid. We're not done at Basalt Vista. The program, the research project with NREL has been completed. We did get our check mark from the Office of Electricity on a job well done. But when you have a living learning lab, there's no reason to put it to bed or end it. So we've been working with the Stanford Linear Acceleration Center on transactive energy projects. This is the idea that I might one day be able to sell my electricity to my neighbor or be able to bid in on electricities. So let's take that dynamic renewable pricing idea where I put a signal out to the grid. At this point, you may be able to bid in on that and say, hey, you know, I'll take that at 2 cents or 1 cent. This has also allowed us to put what I call bumpers on the system. So let's take your EV car for example. You've signed up for our DF program that allows me to manipulate your EV charging in the night. I know that you are parked for 12 hours every night and you only need 2.5 hours of charging because we've been watching you for a year and you're part of our Charge at Home program. Putting bumpers on the system allows us to add member input or consumer input. So let's say that you're comfortable with your EV being charged to 40%. We would definitely take it up to 40% as soon as it's plugged in, but then have the flexibility to take to 100% if we have that oversupply issue, or maybe just take you up to 80%. The same thing with comfort. How much can I manipulate your air conditioning or your heating system? The interesting thing about Basalt Vista is it's a diverse group of individuals who live in the 4 houses for which we manage the energy. Two of the families are from Colombia, and they like it warm in the winter time. And the other 2 families are from Colorado, so they like it colder. But I don't, know which one's in which house, and we only adjust the thermostats a little bit. But being able to set those comfort boundaries really allows us to know actually how much capacity is on the system. We're also working with Siemens. This has a lot to do with security, not only physical security, but cyber security with DERs. This way, if you put the nice security on this stuff, I get a little nervous when a 14-year-old kid gets bored and decides to hook into his PV inverter. So we're working on that. We're also working on PV forecasting. The picture right above there is from our Sunnyside solar farm. It's a 1.8 megawatt farm. And on the other side of the hill, before the mountain's a substation, we're going to put a fisheye camera up there to look at cloud cover to see if we can predict PV curtailment and how much that's going. We also be working on some black start, so the ability for a PV inverter to restart and form a microgrid. That'll be in the lab, and then still continue our efforts with NREL. That was fast. I'm out of slides, but open to questions.
Thanks, Chris. I think one of the questions that I got earlier, I've been answering some of them that I knew as we went, but if you had or were able to show any of the live data feed from the site, from, I believe, your control panel that has, can look at the group of 4 homes and how they're actively consuming at any time?
I can't do that from my house. It is our secure SCADA system that controls the rest of our protection. Right now, we're working on a project to decouple the DERMS platform from our SCADA system as we develop the ADMS. So I could show that, but I would have to log into our SCADA system, and our IT department probably wouldn't like me doing that from my house.
Yeah, well, that's good for a security angle. So next question is, it was, understand that the batteries in Basalt Vista are state of the art. Would the management system work with other battery options? And I'm not sure if that's lead acid or maybe older generation lithium ion, but is there any restrictions on what the controllers can work with on the battery front?
There are restrictions, especially when you get into this software as a service. One of the things we preach a lot about is open source right now. But there are manufacturers out there that claim to be open source just because they have an API that you can write to, but it really doesn't allow you to bring your own controller. So there are batteries out there that you have to buy their gateway, you have to use their dashboard, and then you have to pay them a software as a service fee as a utilities. And some of those can be $100,000. And what we're trying not to do is end up with too many of those companies where we have to pay $100,000 every year for the software as a service to have the platform to be able to signal the DER. So we're preaching pretty hard on open standards and open controls, but a lot of other big vendors out there are trying to understand how they're going to make their economics work when they're offering software as a service. The nice thing about the Blue Planet, Blue Ion batteries that we use inside Basalt Vista, not only a lithium iron phosphate, which is a safer material than straight up lithium ion, they also allow you to bring your own inverter, which was good. So part of Gila Technologies coming to the group was that they had already performed a microgrid called Stone Edge Farms out in Sonoma, California. And it was a stepping stone for us. So we did all this in the NREL lab. We built a Basalt Vista in there doing models, and then we had what's known as hardware in the loop, where you can actually hook up a real PV inverter to a simulated PV load. And we understand how the OPF algorithms were going to work. But we wanted a stepping stone before we went out to the Basalt Vista. So we'd go to the Stone Edge Farms, test it again in a real microgrid setting. And then once we were comfortable with that, we were able to bring it out to Basalt Vista. That wouldn't have happened if we chose a battery manufacturer that didn't allow us to bring our own inverter or even didn't accept open standards.
And Chris, I have a follow-up on that just myself. When you mentioned the open standards, is there a name for it when it comes to energy management?
I think it's being developed right now. I mean, you hear this open ADR, you hear open API. It's really, in my mind, open API is kind of a farce. It means you're paying for a service, a cloud-based service. So it's hard. That's one thing I liked about the microgrid controller, was that we were able to leave a lot of the coordination and communication out there in the field. We didn't have to bring it into a cloud and make a data decision there, or even try to get the data into the cloud so we could know its situational awareness.
Yep. Sorry, there are several more questions that have popped up. Let me get through to these. Okay. Does the Holy Cross Energy control of the DERs provide economic benefits to the homeowners who own EVs as well as the photovoltaic?
The photovoltaic's a little different. At Basalt Vista, we control everything. The houses run normal as they would, pulling power from the grid. They are net metered, so they generate during the day until we make those calls or set them in no modes. And we do that under the distribution flexibility tariff to be able to compensate that. Anybody that signs up for our Charge at Home program, which is the original free EV charger program, they're automatically enrolled in the DF. And that's how we base the economics of giving out a free charger, is the ability to be able to manipulate and orchestrate that load. It's not a huge deal right now, since we only have 160 of those chargers out there. But as we end up with one EV in every garage over the next 10 years, the ability to manage these loads is going to become very important. A lot of this is just building the prep work for the future.
Great. Next question. How did the heat pumps perform for heating the homes? Did you need to use any resistant heat to support that?
Great questions. The heat pumps performed very poorly at first. We were actually surprised, and it got to the point where I could notice it in the 15-minute meter data of which ones were performing. Air source heat pumps, the technology is great. The installation knowledge, when you have an installer come to your house, especially when you're in a mountain community like Holy Cross is, where we don't have a whole lot of air conditioning knowledge of how to install an air conditioner, and a lot of these install like an air conditioner. It's really a challenge when it comes to labor to get these installed properly. So they actually installed them straight on the ground. And then when winter came, the condensation froze and restricted the use of the heat pump, which sent the electric usage through the roof. Since then, it only took about 6 to 8 inches of raising those off the ground to alleviate that problem and give it proper drainage. But again, I chalk that up to poor installation, poor knowledge of actually how to install an air source heat pump, which is what we're seeing in the mountains areas. We need more training on how to do that so we can reduce the cost. But air source heat pumps as a whole are performing very well. We have 2 more all-electric buildings that are coming online. One just came online at the Rocky Mountain Science Center. Again, it's an employee housing unit, all electric, and they're using air source heat pumps, a little bit higher elevation than Basalt. And then Aspen Skiing Company is about to open 160-bed employee housing also that will be using air source heat pumps and CO2 instead of refrigerants for the water heater. So we're excited to see that project come through.
Next question, was there consideration of using ground source heat pumps?
Things I would do over again. Let's start the list. I wouldn't put PV on all the homes. I would build one huge community PV field that would power that whole community. I wouldn't put batteries in every house. I would put the battery right next to the community PV field and power the whole community as opposed to individual homes. You get a little bit more resilient the closer the battery gets to the meter, because you're not dealing with underground or secondary wire or even underground primary. But I think you still get a pretty good resilient approach with having a battery at the entrance to a subdivision. District heating. It's something that we've talked about a lot. There's not a whole lot of it going on in the United States. There's some of it going on in Canada. So right next to that battery, I would have put a large heat pump. And instead of putting heat pumps in every single house, including the hot water heaters, it would have been nice to do a district heating and cooling system based off of one unit.
Okay, great.
Yeah, if anybody out there knows of any district heating projects, especially retrofits, let me know.
What would be a reasonable rebate to incentivize batteries that are controlled by the utilities?
A lot of that has to do with your avoided cost. So every utility is going to have different economics that make sense to them. We are able to find about a little over $100 per month in DF credit based on our economics. So when you look at a battery that might be $130 a month financed over 10 years, that's what we're trying to do, is trying to get to a resilience premium of about $20 to $30, where someone could put a battery in their house, not only save themselves money and have resilient backup power, but also help the co-op and the utility as a whole mitigate some of our wholesale costs and improve our regeneration and flexibility of our grid.
Right. How does the cost benefits of these DER projects compare to, say, a utility scale battery project, which you might have answered there a second ago, but take a second knock at it.
It's apples and oranges. Utility scale is very huge, you know, and it's often coupled right now with PVs. And because of the ITC, income tax credit, you're really kind of limited on the use of them. They're great for taking the duck curve and, as I say, serving it for dinner, that belly of the duck, serving it for dinner. So taking the energy from the day and moving it to the night. They're great at doing that. But if you're trying to mitigate some oversupply of wind generation, the way some of these contracts are set up through the PPAs, you just can't do that until the ITC is let up. Or you have to have provisions in the PPA already in place with thought this actually might happen, that I might want to charge this battery from the grid because it actually could be cheaper than charging it from the PV.
Great.
Good question, though.
Next question is, have you considered offering, security packages like ADT wrapped into, the smart home devices so the sensors could actually provide security service?
A good idea. I hadn't really thought about that. It's having a DER controller in your house, and we're updating Basalt Vista, so we don't need one controller per DER. We're getting to the point where we only need one controller per house, which is nice. But at some point, every house will have a gateway, and that is a device that links a DER or even a meter to your Wi-Fi network. There's a lot of advantages to this. You can get energy monitoring systems that show you real-time data, but not only show you real-time data on your phone, but have access for me to visualize your real-time data through a cloud-based platform. Again, a software as a service, but a good software and a good service. I think as these gateways become more prevalent in people's homes, and every Tesla Powerwall now comes with its own gateway that monitors your energy and your house energy, your battery energy. I think the ability to hook up other systems, smart devices, smart plugs, even like a smart lock on your house will be fairly easy.
Great. Next question. To what extent do the homes use passive solar heating and building thermal mass to reduce winter heat load?
Not as much as they should. But like I said, the first idea out here is to build a tight envelope, to make sure that you have energy efficiency in place before you energy optimize, because there's no point of optimizing energy in a house that's leaky or has holes in it. I don't know the requirements or exactly how these were built down to that T. That's not my expertise, but we could put you in contact with somebody that does. I think Marty Treadway is actually on this. Shout out to you, Marty Treadway. Thanks for all the help on this project. And he might be a good resource to ask about that.
Okay, so one of the early slides mentioned that coal was about 50% of your load, and I guess asking how that will be brought down so significantly by 2024. Are you?
Great question. Someone's paying attention to my slides, so thank you. We've entered into a contract with Guzman Energy. They're based out of Denver, Colorado. They're an energy broker. So they're taking our coal and replacing it with renewable generation, and then taking that coal power and reselling it back on the market. We are stuck with the emissions from that. So part of our 70-70-30 plan was to reduce our emissions by 70% also. So that's something we're working on, is how to reduce the emissions that are technically ours from that coal plant, even though we're not receiving the energy. So there's still a pretty big market out there for coal for people that are trying to keep their rates down. We'll see what happens with that.
Okay, next question. How is anti-islanding being handled in an era of managing DERs so that power isn't being fed to the grid during times when repairs are being performed to the grid? Yeah, a lot of that is based off what you know as your situational awareness. So that's your ADMS talking and knowing exactly what's going on in the system. Anti-idling has always been an issue. I've heard horror stories even on our grid of PV inverters coming back online. One of the situations was that we tried to keep the lights on, so we rolled the diesel generator. And when we turned that back on, the PV caught the pulse, as I call it, from that generator in the grid, and it kicked on. Lucky our lineman caught it in time, and we're able to shut everything down. But it's scary. Anti-idling, it scares me, and I think it scares linemen too. But you know, smart inverters are coming a long way through Rule 21 and Rule 19 that have created this smart inverter that is grid interactive, and it definitely provides us a lot of data in the ability to perform anti-islanding at an inverter-based level, as opposed to having to build direct transfer trips from our substations or our reclosers to large PV fields. Okay. Next question. Residential solar creates voltage violations. Is it better to curtail solar versus power factor control at the inverter versus traditional solutions like distribution reactors and voltage regulators?
Yeah, great question. Good technical question. I always enjoy those. My opinion, voltage regulators are a thing of the past. Batteries and DERs, if managed properly, will provide all the voltage and frequency support that you will need in the grid of the future. We're working on flexible interconnections with the ability to curtail PV if we need it. Our system has a lot of long lines up long drainages. So you can imagine that our valley has a river in the base of it and a road next to it, and every secondary and tertiary creek that seems to feed into that river has houses on it. So we have a long line of radial single phase lines going up into the mountains. The problem is a lot of these people want to be renewable, so they put pretty big PV fields up there at the end of the line, and those PVs have to push pretty hard on that line to get power back into the grid, and that causes voltage to rise. So the ways to mitigate that, like I talked about, are flexible interconnections. I think those are coming. But even just the ability to take a battery out there and put the battery next to the PV and say, hey, I'm going to have you charge during the day and just discharge every day, just like arbitraging time of use, but you're really arbitraging voltage violations on the grid.
Great. Were you able to help offset the additional capital costs, or were you able to help offset the additional capital costs required to build out the homes?
No, I mean, to build an affordable housing community is tough, especially in Basalt, where the land's high, utilities are high, asphalt's expensive, everything's more expensive. This was an all hands on board, everybody's checkbook out kind of project to set the example of what could be done. You know, as they get into phase 2 and phase 3 of this project, each phase having 9 homes each, they have figured out ways to reduce costs. But again, a lot of it's just, you know, over 20,000 people have volunteered out there and pounded nails and stained wood just to build these homes. It was really a community-led effort. As I say, it takes a village to build a community.
Great. As you acquire new generation, what considerations do you have in terms of local generation versus that which must be imported? And within the context of local, what must you think about in terms of ultra local, say in the upper Roaring Fork Valley or in the Newcastle area?
Yeah, it's great. We could never hit the 70% renewable goal with local generation. There's just not enough square footage. There's not enough area. There's not enough roof space. It's just not possible based on it. You just can't shove all the generation in Newcastle because each transformer can only take 10 megawatts worth of generation, or each feeder coming out of that transformer. So you talk about some pretty dramatic system upgrades that are needed to support local generation. So, you know, as Holy Cross, we have to take a step back. It'd be really hard to meet our goals inside our footprint. So we defined our local, what's local to us is the Colorado state boundary. And I think that makes sense for us, and I'm happy with that decision. But again, you know, the goal is to also build generation inside our territory. We've had, I think, 1,600 rooftop PV installations over the last 5 years. So PV is coming on. Now we can get to couple that with some other DERs and some other control algorithms, and you're able to cluster DERs now into groups and have them act like Basalt Vista, where you can put a power signal call out to a certain area and either have them go into a net zero energy zone or have them perform a function like peak time rebate. So I think every utility is going to be a little bit different, but you know, we're lucky that we're not Hawaii and we're not completely islanded. So we have the ability to go to the Front Range and build wind because we could never build wind in this area. It blows too erratically or not at all.
Okay, the next question is a little bit complex. I think I'm going to try to paraphrase this one, but I think it has to do with when you're aggregating the 4 houses. How are you handling the metering there, or you know, when they're, I guess, all islanded? Is, you know, if one house overproduces, you know, how are you balancing that out?
Yeah, it's not meant to financially balance out. Meter to meter, they're meant to act as an aggregate itself. So we provide credits through the DF tariff for the ability to manipulate the charging. They're also net metered, so they do have very, very low electric bills. If we size the PV right, they wouldn't have any electric bills and they'd be truly net zero. But it gets to the question of what exactly is net zero? What does that mean to you? And I've asked myself and a bunch of people this question many times. And that idea that net zero is only that you generate as much electricity in a year as you consume is kind of an older idea to me. I think net zero is kind of falls into this energy optimization where you're really doing a better part to the grid and really helping the grid become, or community become net zero as opposed to just 1 meter. I know that doesn't quite explain the question of how we deal with net metering in a grid interactive house, but we're still working on that. But a lot of the compensation is done through what's known as the distribution flexibility tariff.
Great.
Which you can read about in our specs. If anybody wants to read about any of the programs, the full write-ups in our rules, regs, and tariffs that can be found at holycross.com.
How much additional effort is needed from HCE to manage Basalt Vista from a utility perspective, and how scalable and economic do you think, you know, this project is?
Excellent question. I do believe the project is scalable. We already are talking to other habitat communities looking at the same type of design and architecture. We're also talking to other utilities that are performing a lot of these same functions. It might be a unique and novel idea, but I'm not the only research engineer out there working on this. So there's a lot of projects going on, some in North Carolina, at the North Carolina Electric Co-op. Heron's Nest is one of theirs. There's also some projects going on up in California, or I'm sorry, Canada too, that are kind of taking the same approach of how do we build an hierarchy on the grid of command and control. And that was the basis of Basalt Vista, and there's a couple different ideas of how to build a hierarchy. The 2 most prominent, one coming out of PNNL, a research lab, and it's called a hierarchy architecture. And then the other one coming out of NREL is the OPF, real-time optimal power flow algorithm. And let's just talk about the OPF algorithm, because that's the work we did at NREL inside the lab. So if you just step back and keep on zooming out, so most people, if you hired a distribution engineer and said, I want you to build me a feeder, the first thing they would draw on the map is the substation. And then they would draw a line out and they would build a home, and then draw another line out and build a load, and draw another line out and build a load, and then they continue on until the end of the line. Basalt Vista kind of flips the switch on that, where we started the design at the house level and then started moving back towards the substation. So what's beautiful about the OPF algorithm, like I said, it's the same algorithm that runs on the coordinator, runs on each individual DER. But you can move a step back from that. And the best way I can talk about this is what's known as a fractal grid. So if we all think back to mathematics that we took in high school and college, and we all kind of remember what a fractal is. It's a shape that repeats itself with the same geometric pattern. So if you zoom very into the far ends of a branch, it would look like the same picture from when you were completely zoomed out. And the same architecture could be true for a grid. So not only do I have an OPF algorithm running at the house, I have an OPF algorithm running at the transformer. And then let's just keep on taking it up a step. I have an OPF algorithm running at the subdivision head. And now I have an OPF algorithm maybe running in the town. And then above that is an OPF algorithm that runs at a feeder head. And instead of making a call to the transformer like I do for 3,000 watts, instead I make a call to the substation. And I say, hey, substation, I want 3 megawatts. So the substation knows the whole hierarchy and knows the availability of all the DERs under it, because that's the OPF algorithm, how it rolls up. The same way the coordinator knows the capacity of all the DERs inside those homes. The substation coordinator would know all the aggregated capacity of all the smaller coordinators or the generals below it. So as you roll that up, you end up with this fractal shape where it's the same algorithm working on every single level. So if the feeder head loses power, the commanders and generals under them know what to do. And if you end up with having a net zero energy zone that has the ability to microgrid, that's when it would microgrid. And that's kind of the beauty of this architecture, is that no matter where the power is coming from, there's enough situational awareness out there that the homes know which sub and which feeder they're connected to, and are able to follow the hierarchy of commands out in the field.
Okay, Chris, I've got a clarification. I actually misread a question earlier. The question was, well, the intent was, what are the economics for customers without electric vehicles or photovoltaics, i.e., is this benefiting the entire system and them as well?
Yeah, so we save 25% of the costs or the economics of the DEF for the membership as a whole. It also allows us to increase our renewable energy mix. And as we all know, RE fuel right now is cheaper than coal or natural gas. So it creates not only a great benefit for the member, but it's also a good benefit for the community. And I think being at a co-op, we have a little bit different mindset on that. And then we have I would say a better relationship. I find it funny when you get on these webinars and you hear these big IUs talking about becoming member-centric or customer-centric. To me, they're just trying to be a co-op.
Great. I know you kind of addressed this earlier with the district heating, possibly using a ground source heat pump, but did you consider them for the individual units at all?
We did not for this project. One of the reasons is in the homes or right behind the homes, there's a pretty big underwater culvert, which is ditch running through it. So it would have been kind of hard to plumb that to all the homes. We are looking at some other projects around the Aspen Airport, and even contemplating what a geothermal runway might even look like with some district heating. We were awarded a Colorado DOLA grant to perform a feasibility study on what it might take to perform district heating and build an energy optimized corridor in the Aspen area. So more to come.
Great. Are the heat pumps, are those mini splits?
Ductless mini splits, yep. Carrier donated them.
Great.
Which, yeah, was difficult. We'll just hit on that for a second. So a lot of these hot water heaters and air source heat pumps are coming with what's called a CTA 2045 port. And this was a port designed by EPRI that was supposed to make it fairly easy for utilities to control that asset. You know, A.O. Smith's hot water heaters come with this. Mitsubishi's heat pumps come with this interface, but the carrier units did not come with that. And because we're trying to do all local control using, you know, microgrid technology, we've adapted to now using Nest thermostats. But, you know, the first part of this program, we went rudimentary on it and actually had a demand response controller on the heat pump to kill the power. It's, again, my belief that we shouldn't be really working on demand response. We shouldn't really be turning things off and on. That's a very old and archaic way of doing it. We should really be focusing our efforts on flexible assets.
Okay, next question. Is it possible to know more about the structure of the homes, i.e. the HERS rating, wall and material insulation, HVAC specs, etc.?
You know, I have all that information. Feel free to send me an email, or like I said, if Marty Treadway's out there, send him an email. He'd probably know better than me, but I'm more than happy to talk about this offline of what the specs are on those homes.
Okay, next question is, why would you prefer one large solar farm battery to power all the homes instead of one on each roof?
Because inverters have a tendency to fail. And with one large battery inverter, I'm only, you know, if it comes in 3-phase, I have 3 inverters. So I'm really only controlling 3 inverters as opposed to 27 inverters. It reduces the overall costs. It makes it easier to control. And it's the same way that the reason you would build a utility scale, just economics of scale and the ability to control one asset as opposed to everyone's. You know, ideal world, ideal future, if I could do it, even go back in time and do it all over again. I really don't like PV on roofs. I understand the need for it, and I understand this is how we got here. And through adoption, we've grown into this net metering approach where we're going to put PV on the roof. It's tough to control. It's just, you have to take it all the time until flexible interconnections are developed, and the costs that you have to pay for that PV in the middle of the day when I don't need it. You know, it just makes the belly of the duck even worse. So yes, I wish we could go back in time and just build giant 1 to 5 megawatt PV fields everywhere.
Okay, great. Next question. It was very interesting that you mentioned that you might not need to control all of the fleet of DERs and that it is substation dependent. Any other thoughts on whether other utilities would see that, or is that a peculiarity of the HCE and Basalt of that part of the grid?
No, I think every feeder is going to have its own profile, its own characteristics, and its own you know, difficult areas. A lot of it has to do with how we designed our system, right? It's I call it one span at a time, because that's what happened in Aspen. Was that someone would move into a house, you'd build 200 feet of poles and wires to that house. Then 2 years later, someone would move in next to him and you do another line extension, 200 feet to another transformer. And that's kind of the way the whole system was built. There were some, big parts that were done in series to get power into the real rural areas. But, that's the kind of the way it was designed. Because of that, you're going to end up with the remnants of that. Where someone may have not chose the right proper wire size, or there might have not been the best engineering analysis, where you could have seen a tremendous amount of load growth that you didn't expect in a certain neighborhood. This could also be, expedited by or exponentially affected by EVs plugging into one neighborhood. We often talk about the neighborhood effect, and we see it a lot, where someone will get a PV, and then the neighbor has PVs, and same thing with EV. Someone will bring home their new Nissan, and And then next thing you know, the neighbor's gone out and bought a Nissan Leaf too.
Okay, here's a follow-up on your previous answer on the ideas like district heat, community PV, and the battery. Any suggestions for creative financing to offset, such a large upfront capital cost for a small group of homes or a community?
That's hard. We've come up with some rebates. We're working on beneficial electrification rebates for that sole purpose to try to reduce the upfront cost. But that's also one of the reasons we developed the distribution flexibility tariff, was to be in the DERSA, the DER service agreement, was to potentially be able to finance a project like this over time, and to be able to have them make monthly payments on it, while we also pay for what advantages the utility has and economics the utility can have off of managing that DER.
Okay, next question. How big is the Basalt Vista community going to grow, and how do you see this approach scaling with that growth?
Yeah, well, Basalt Vista is slated at just the 27 homes. The nice thing about Habitat is they do own the architectural sets for those homes, so they can take that and build that at another location. There's a lot of land still around this area in Basalt, a lot of farmland that could be used to develop it. Basalt Vista will be capped at 27. There will be more Basalt Vistas out there. They're not going to be called Basalt Vista, but Habitat will still be building homes, and we will still be looking for ways to make them very economical to live in, which is one of the biggest benefits. As someone that lives in an all-electric home, I understand that if I turn on too much load, it will dramatically affect my bill, and that's something that we preach and we talk about to people living in new all-electric homes, is that if things are done wrong, these things can consume a lot of power, just like the heat pump. If it was installed wrong, it consumes a lot of power. So a lot of our approach was not only to build affordable housing, but also build affordable housing that was affordable to live in. And I think that idea is just going to continue forward. I look at some trailer parks too, of what we can do then in there. Can we take out these poorly insulated trailer parks with holes in the walls and the floors, and bring in a prefab, but again, do that PV on site and that battery storage on site. So not only they can have benefits from that economically without having any upfront costs, but they can also provide a service to the whole community, the whole membership.
Great. Are the homes LEED or Department of Energy Zero Energy ZERH rated?
Nope, neither one. LEED's very expensive to go after, in my opinion. I couldn't imagine an affordable housing community going after a LEED score. That seems a not good place to put their money, but each into their own.
Okay. Obviously, the engineering overhead for a system like this, especially the initial homes, was large. Can we expect this cost to come down substantially? And how do you assess the possibility for a cookie cutter housing development using this model?
Yeah, I think it can come down. I mean, a lot of it's just was in gaining knowledge and research. The actual price of the assets, an electric hot water heater is not very expensive. Heat pumps, minus the labor that it takes to install them, are not very expensive. EV chargers, again, I should tell the story. The first people that moved into the house, these guys won the lottery. The first, all 27 homeowners, but they applied to a lottery and they won. And the first 4 homeowners, they didn't understand that Habitat had agreed to allow a utility to control those homes. So they kind of came into it a little blind, but they're teachers. And I got to know them very well, and I would tell them about the project and what all I was going to do, and really built a great relationship with them to allow me to gain trust, which I think a lot of it is. So I think, for these projects to move forward, the economics have to work. For Holy Cross, the economics did work because we do pay a peak demand charge. And to be able to mitigate that peak demand charge is how we base a lot of our economics around, not all of our economics, but a lot of our economics. But for every utility, they're going to have a different economics, and for every employee housing developer, they're going to have a different mission statement. This mission statement was to set the example, for which we did, and I'm proud of that.
Okay, great. I think this is the second to last question, I think. If the storage and EVs would be used for energy storage for use in the community, how are the EV owners compensated for the faster aging of their battery packs due to the increased number of charge-discharge cycles due to supplying the microgrid, in addition to the cycles that occur strictly for transportation?
Excellent question. Just had a conversation yesterday on this same topic. We are not currently doing vehicle to grid discharging. The discharging of the batteries is from a stationary battery bolted to the floor. It's not from a mobile battery you can drive around. We're still waiting on IEEE and ISO standards on how to do V2G. I think it's coming. I don't know how long. I would say 5 years if I had to guess. But you know, Elon had V2V, vehicle to vehicle, figured out in 2008. He also knows how to put PV on the roof and batteries in the garage, but yet has not figured out how to take that 60 to 100 kWh battery sitting in the driveway and discharge it into the grid. So, you know, if Elon can't figure this out and is building power walls, it just kind of points to me that the industry is just not ready yet.
Well, great. Well, I think those are all their questions. I wanted to make just a quick comment based upon, it was a question earlier about, you know, financing like district heating. I don't have specifics on this, but I recall reading about it was a large new home development, I believe outside of Austin, where I think they either the HOA handled it or they might have created, you know, maybe it's like a metropolitan district or something, or a small utility, but they put in large ground source heat systems that provide district heating and cooling to the neighborhood. You can probably just Google it. I think Bosch did the ground source heat pumps, but it seems like, you know, it's the one I've heard about. But, you know, basically for a new home development, it's a sort of amortized into, you know, across everyone's cost, and you basically pay for your heat and cooling, and that funds, I guess, the investment. But if no one else has any questions, just want to thank.
Only 2 gas lines to everybody's house, and then we could use one for hot and one for cold. So
yeah. Well, anyway, Chris, I want to thank you so much for a great presentation and taking your time with us tonight. And I want to thank everyone for joining us. Just a reminder, we will be sending out the recording to all the registrants. And then, of course, you can find it if you want to share it with folks. It will be posted to the CREST YouTube probably within the next several days. So, Chris, thanks again. And
yeah, Peter, thank you, and thank everyone. It's not too often I get a lot of good questions like that. So ask a research engineer questions is kind of fun for me. So I appreciate everybody's engagement on the call. And if anybody has any further questions, feel free to follow up with me. And if you're in the Basalt area, and drop in and take a look at the homes. They're absolutely beautiful, and maybe give me a call and I might be able to show you some of the technology.
All right, thanks again. Everyone, have a great evening.